Okay, everyone. Y'all ready? All right, so hopefully you submitted the test. I'll hopefully get going on those the next day or so, get those graded. But we are going to continue now. Actually, we're going to finish up a problem that we had started at the end of class last time. So we had talked about this new test for convergence and divergence of the series, and it's called the integral test. So this is the problem we are working on, and I had told you that, you know, the first thing you want to do is go through all the things you already kind of know. All right, so we know the nth term test. That's the first thing that you should usually look at. And for that, what you're going to do is just take the sequence, okay, which is the expression that's in the series, and take its limit as n goes to infinity. Oops. And this is going to go to 0. I mean, we can check that with L'Hopital's rule, but that goes to 0. So this is that pregnancy test thing that we talked about. So this fails, right? Anytime that goes to 0, it's a failed test, so we have to move on. It's not geometric, not a geometric series. We know that because we don't have the n up as an exponent. We would need that to be able to say it's geometric. So it's not geometric. It's not harmonic. It's not harmonic because we don't have a constant over a linear expression, so it's not harmonic. And then the last thing is maybe it's telescopic or collapsing, but it's not that because we can't factor the denominator. N squared plus 4 cannot be broken into 2 factors. If we could factor it, then maybe we could do partial fractions and then see some sort of canceling, but that's not going to happen. So everything has failed. So that leaves us really with the only other thing that we know, which is what I'm introducing you to, which is the integral test. So the integral test says what we're going to do is we're going to look at the sequence, and we're going to rewrite the sequence as a function of x instead. And now we have to check a few things. So I have this is directly copied from your formula sheet. The thing we have to check on the function is that it's continuous, positive, decreasing, and integrable. So first of all, is it a continuous function? And remember, we're only looking at this function on the interval 1 to infinity. And the reason we're only looking 1 to infinity is because our series, right, starts at 1 and goes to infinity. So we are looking at the function instead of all the dots, we're looking at the smooth curve. And the conclusion that we'll draw here is that whatever the integral does, that's what the series does. Okay, so we're only going to look from 1 to infinity. So if we look at this, let's check for continuity. Is it continuous? Well, yes, because there's nothing that makes this thing undefined, right? We never get division by 0. We never get square roots of negatives or anything like that. So it should be continuous everywhere. Is it positive?
What test is this?
This is the integral test.
Oh, okay, got it.
Okay. So is it positive? So is that always going to give you a positive number? Well, what do you think? We're going to plug in values for x, right? But these values are going to come from the interval 1 to infinity. So we've got to be plugging positive numbers into the top. In the bottom, it really doesn't matter because we're going to square it and add 4. So that's going to be positive. So no matter what, we should have a positive number divided by a positive number. That should be positive. And so we've got that condition met. Then we have to show that it is decreasing. And this is where we had done this part last class. So to show that it's decreasing, there's 2 ways to do this. You can go back to the sequence and show that the sequence is decreasing, or you can look at this function and show it's decreasing by showing that the derivative is negative. Because anytime you have a negative derivative, that means your function's going down, right? And so I just would take the derivative of this function. We did this in class, okay? So the derivative would require the quotient rule. And so if I do the quotient rule on this function, I get this, and then that I think simplifies to be, let's see, 4 minus x squared over x squared plus 4 squared. I know that the denominator is always positive because I'm going to take some number and I'm going to eventually square it. And now the numerator, this is a little bit weird, but is the numerator always negative? Remember our domain here. So like, what if I plugged in 1? If I plug in 1 for x, isn't that going to be positive on top? Right? And if I plug in 2 for x, I'm actually going to get 0 on top. But once I get to the number 3, this term right here, x squared, when I take 3 and square, I'm going to get 9. 4 minus 9, that's going to be negative. So do you all agree that this is negative, okay, eventually? And then once you get past 2, like once x gets past 2, that's always going to be negative, won't it, on top? So that's all you need. And sometimes I tell my students to come back up to the formula sheet, and then where it says decreasing, just put here like eventually. Because it doesn't have to be decreasing the entire time. It just has to be decreasing, you know, from some point on. Does that make sense?
Yes.
Mhm.
How did we look for the decrease?
What?
No, I got it. Because you had the page on the upper end, so I wasn't able to see the derivative.
So we're good?
Yes, sir.
Okay. So we now have concluded that we are going to eventually be decreasing. The next thing I have to show is that it's integrable. And by checking to see if it's integrable, we just need to know, can we integrate it, right? So here comes the integral we're going to do. Integral from 1 to infinity of the function x over x squared plus 4 dx. So you look at that, and now you're just asking yourself, can you integrate that? Now we can, right? This is something we should be able to do with the basic u sub. You'll see that the denominator, if we let that be u, the derivative is 2x, which we're off by a constant. So we should be able to integrate this. But I'm also going to have to convert this into a limit as t goes to infinity, integral 1 to t. So that step right there, I'm doing this because I have an improper integral. My integral has as a limit of integration infinity. So this is an improper integral type 1 when we covered these. Anytime you have a type 1 improper integral, we have to replace the infinity with t and then let that t go to infinity. And then I need to integrate this. Now I'm not going to spend any time on the integration here. I'm just going to trust that you can do this integration. So we're going to have limit t goes to infinity. Okay, here we go. The antiderivative of this should be 1/2 natural log of x squared plus 4. Y'all trust me that that's right?
Yes.
Okay. And then we're going to go from 1 to t. And now we plug in t, and then we plug in 1 and we subtract. So when we plug in t, we get 1/2 natural log of t squared plus 4.
Is this the same concept from improper integrals?
Yes, exactly the same. Yep. Okay, there we go. So we are plugging in t, and then we plug in 1, and let's see what happens to this. This right here at the end is just 1/2 natural log of 5. We don't need the absolute value, but I'll put it there. Now what happens as t goes to infinity here? It becomes infinite, doesn't it?
It's going to infinity, positive.
Right? And then natural log of infinity would also go to infinity.
Yes.
So half of that this thing's all going to infinity. And so what we have is divergence, right? This means that this integral diverges.
So what if the natural log was going toward was a 0? Then it's negative infinity.
That would still diverge then, yes.
Yes. Okay.
So our conclusion here is that the original series diverges. Therefore, the original series diverges by the integral test. Any questions?
So we need to show all of these steps before we see if it's integrable to get
Yeah.
the divergence.
Yeah, so I was just going to mention that if you ever run the integral test during an exam, you need to show that it's continuous, positive, decreasing, and then you can get to the integral. You can't just go straight to the integral because you can only run the test if these things are met, these conditions are met. All right, so let's look at it just to have a look at what this sequence does and what the series does. All right, so on the left side here, again, is the sequence of numbers. And you can see that the sequence goes to 0. We knew that. The series is us adding these all up, and you can see that the series, the sum, is getting bigger and bigger and bigger. And it looks like it's growing without any bound, right? It just keeps getting larger and larger and larger. So it's not this sum here is not like becoming asymptotic. It's not converging. All right. Let's do another one. So the question here, oh, by the way, do we know what this series converges, or never mind, it doesn't converge, sorry. It diverges, right? So I was going to ask you, do we know what it converges to?
No.
So we don't, but that's because it diverges. If this integral would have converged, right? That tells us that the series converges, but it does not tell us what it converges to. As a reminder, there's only 2 types of series that we can ever find what it converges to. That's a geometric series because we have a formula for it, and a telescopic because when we do all the canceling, we'll take a limit and we can get a number. All right. Okay, here's the next example. So the instructions here are, does this converge or does this diverge? Now, another way you could write this, if it makes it a little easier to look at, is dropping the e to the n down to the bottom like that. So if I were doing this problem, I would run through all the different things, right? Nth term. Let's see. Let's take the limit as n goes to infinity of n over e to the n. That's infinity over infinity. So if I do L'Hopital one time, and I will remind you that I'm doing L'Hopital here, but remember, technically, I'm supposed to make this a function of x because you can only do L'Hopital on functions of x. But because that's in the past now, I'm just going to say, yeah, we could get to L'Hopital to get to this result, right? Derivative of the top and bottom separately. And now this goes to 1 over infinity. That goes to 0. So that means the test fails. Any questions? We're okay. Is it geometric?
No.
No, but I mean, we do have an n up in the exponent, don't we?
Mm-hmm.
We do. But that's not the only thing that we have. We have an n here. So if that n wasn't here, if that was like a number like 4, then this would be geometric. But it's the fact that we have something that's not a constant along with this that makes it not geometric. All right. Is that clear to everyone?
So even on the left side, because like before you simplified it.
Yeah, even on the left side, because this n, that n right there is not a number.
Okay.
Right? Geometric requires this. right? So that has to be a number. And then this has to be a number raised to a power. Well, we have a number raised to a power, right? E to the negative n, that is this piece, right? But the thing that's out in front is not a constant. So we can't use it. So geometric, no. Is it harmonic? What are we looking for harmonic?
Not linear.
Yeah, we need constant over linear, not harmonic. Telescopic, don't think there's anything you're going to be able to do, like in terms of like partial fractions or anything like that, to make it split up into something minus something. So we're stuck here, okay? So now, if I were doing this problem, the next thing I would ask myself is, could I integrate that? If I looked at this as a function of x, could I integrate it? If you don't like that version, then you could write it as this. So could you integrate this?
Yes.
Yes. Yeah, that's parts, right? Integration by parts.
By parts, yeah, that'd be integration by parts. Okay, so we can integrate it. Let's just make sure it qualifies. So first of all, is it continuous?
Yes.
Yes, it is, because this is defined for every x. You'll never get division by 0. Is it positive? Well, remember, we're only looking at the interval 1 to infinity. So if I plug in a positive number on top and plug in a positive number here, this is all going to be positive. So that's yes.
So where are the cases when this would not be continuous?
Let's say you had division by 0. Okay, so let's say we had this expression right there instead.
Okay.
Then if I try and plug in 0 here, right? E to the 0 would be 1. And 1 minus 1 would be 0, right?
Okay.
But I couldn't plug in 0, but that actually wouldn't matter because our interval is from 1 to infinity, right? So 0 would make this bad, but I'm only looking 1 to infinity, so this would still be good. I'm just trying to illustrate that, you know, you're looking for things like division by 0 or square roots of negative numbers.
Anything that makes it undefined.
Anything that makes it undefined, correct. As long as that, you know, happens between 1 and infinity, then you'd have a problem. All right, next thing is it decreasing? And for that, I'm going to take the derivative and show that it's negative. So I'm going to do the derivative this way. I'm going to do quotient rule on that, on this. I'm going to do quotient rule. So derivative of the top times the bottom minus derivative of the bottom, which is itself, times the top all over the bottom squared. Okay, the top is going to be e to the x minus e to the x times x all over e to the x squared. Okay, one more thing here. I'm going to factor in e to the x at the top. And now I'm just going to think about this. The denominator is always positive because anything squared is going to be positive, right?
I have a question. So in order to check for decreasing or increasing, what do we do again?
You're going back to Cal 1 and you're saying decreasing functions require that the derivative be negative, right? Because if the derivative is positive, your function's going up. If the derivative is negative, your function's going down. If your derivative is 0, it's flat. So all we're doing is trying to show that this function has a negative derivative, which means that it's going down or it's decreasing. So I take the derivative, and now I just need to convince myself that this expression is always going to be negative, or eventually it will be negative. So the bottom is positive, right? What is e to the x? E to the x is always positive, isn't it? E raised to any number is always positive. Just think about what e to the x looks like, right? That's e to the x. It's always above the x-axis. So that's always positive. Now, what about this number? 1 take away x.
That could be negative eventually.
It's going to eventually be negative, right? Now, if I plug in 1 for x, I'm going to get 0, right? But
Mhm.
anything bigger than 1, this thing's going to be a negative number, right?
Yes.
So this is going to be negative eventually. And then once you get, once x is bigger than 1, that's it. It just stays negative the whole time. So I would say we are decreasing, okay? All the conditions are met. So now we get to do the integral. Integral 1 to infinity. I'm going to write it this way, x e to the negative x dx. And I think this is a good opportunity for me to go to the side here, and let's just do that integral. Let's do it as an indefinite integral. That way we can do our integration by parts. Then we'll come back over here. So when I do integration by parts, I've got u, dv, v, and du. All right, so I'm going to let u be x. dv will be e to the negative x dx. I'm choosing u to be x because when I do integration by parts, that x is going to become a 1, and that's going to make things nicer, right? 1 dx. And when I integrate e to the negative x, be real careful on that. The antiderivative of e to the negative x is negative e to the negative x because of chain rule, right? If you took the derivative of this, you need to get this back. So you have to put a negative out here to kind of take care of that negative when it comes out with the derivative. And now my answer should just be ultraviolet minus voodoo. So I'm going to do ultraviolet. Here's ultraviolet. Minus the integral of voodoo. And voodoo is going to give me another negative. I'll just do it in here. Negative e to the negative x dx. So that's your voodoo right there. This becomes negative x e to the x plus integral e to the negative x dx. So I just move that negative out here. And then let's find that antiderivative, which would just be, again, negative e to the negative x plus c.
Wasn't that first e to the x supposed to be e to the negative x?
Where?
The left side of the.
Oh, yeah, I forgot to bring down. Thank you. That's negative. That's negative. Thank you. Right here, right there. I forgot that negative. I had it on this one. I just forgot to bring it down. Okay, now we need to convert this over to an improper. So it's going to become a limit. T is going to go to infinity. And we're doing integral 1 to t x e to the negative x dx, which is equal to the limit. T goes to infinity. Okay, the antiderivative is negative x e to the negative x minus e to the negative x evaluated 1 to t. I can remember when I was in Cal 2 learning this integral test, I didn't like it. It's just long. Okay, so now I'm going to plug in t, and then I'm going to plug in, what, 1? Okay, when I plug in t for x, I get t e to the negative t minus e to the negative t. Then when I plug in 1, I get minus 1 e to the negative 1 minus e to the negative 1. Ay, ay, ay. Are we happy?
No.
No, right. I like honest answers. Okay, when I do this limit, I realize I have some issues. I'm going to just rewrite this here. Negative t over e to the t minus 1 over e to the t. I think it'll be a little easier for me to deal with that limit that way. Negative 1 over e minus 1 over e. So all I'm doing is using these negative t's and dropping them down, right? And now I'm going to let t go to infinity. You ready? Here it goes. Let's take care of the easy one first. This one goes to 0, right? Fixed number over something that gets infinitely big, that goes to 0. What about this one, though? The top's headed where?
Negative down.
Negative infinity. Where's the bottom headed?
Infinity.
Infinity. So we have infinity over infinity, right? L'Hopital. So derivative of the top would be negative 1. Derivative bottom would be itself. And now run the limit again. So what would happen to this limit here? That would go to
0.
0. Okay. So that goes to 0, that goes to 0, right? And then these, nothing happens to these, right? So what do I get there? Those two together, that's -2 over e. But I still had a negative in front, right?
Mm-hmm.
And then that together becomes +2 over e. So all of this becomes 2 over e. And isn't 2 divided by e a number? Right? So
Yeah.
so that means it converges, right? The integral converged. And according to the formula, or to the test, if the original integral, right, if the integral converges, then so does the series. Therefore, this series converges. Now I'll ask you, does the series converge to 2 over e?
No.
No. The series converges. That's all I know. I don't know what it converges to, though. I just know it converges. I know what the integral converges to, but that's not the same thing. The integral is not the same thing as the series. Okay, what do y'all think? It is what it is, right? It is what it is.
Yep.
I genuinely fear the next test.
Yeah. Next test. Actually, this isn't even a test. This is actually just a formula, which is really nice. So P series. So here's what we have. If we have any series that looks like this, 1 over n raised to p. P stands for power here, like the power on the n. That's a weird P. Okay. Then look at what it says. This series will converge if p is bigger than 1, and it will diverge if p is less than or equal to 1. Now, I'm not going to prove this. And sometimes if I have enough time in a class, I will prove this, but we just don't have enough time. So let me just show you this in action. Example. Does this converge? I'm just going to put C/D to mean converge or diverge, okay? So I don't have to write it over and over. Okay, so sum n equals 1 to infinity of 1 over n to the 3rd power. Does that converge or diverge?
Converges to 0.
Goes to 0.
Converge.
This is a P series. What's P? The power on n is 3, right? And
So
according to the
converges.
formula, if P is bigger than 1,
It converges.
converges. All right, you don't need to show me anything else. That is a convergent series. Another example. One over the cube root of n.
Diverges.
Okay, so this is a P series, isn't it? What's P?
1/3.
1/3. So you have to realize that the cube root of n, right, is actually n raised to the 1/3. So this is a P series, and that P is less than or equal to 1, and that means we have divergence.
So what if it was under cube root whole square?
Like that? Is that what you mean?
Yes, sir. I think
Okay.
it converges, right?
No, it
Well, what's P?
diverges.
This would be n to the 1/3, but then squared, that's n to the 2/3, right?
It's still less than 1.
So that's still less than 1.
Less
That
than
P is 2/3. That's less than 1. If it's, sorry, less than or equal to 1, anytime we have that, we have divergence.
Okay.
Here's one. You may recognize this. What type of series is that? I mean, I know it's a P series, but before we talked about
Alternating? Is that an alternating series or the sequence?
no. What do you have there? What over what?
1 over n.
Okay, one is a
Constant.
Constant.
over linear. Constant over linear is what we refer to as
Harmonic.
an all harmonic series
Or divergent.
diverge, right? But now you can see kind of why, because the power on this is 1, isn't it? So this is really a P series with P being 1. And according to the formula, if your P is less than or equal to 1, you diverge. So that is why on your formula sheet, you don't have anything on the formula sheet that talks about harmonic series. And the reason why is because it's covered right here in P series. If that P is 1, then you are less than or equal to 1, you diverge. So a harmonic series is a special case of a P series when P is 1. That's all it is. Okay, how about this? Oops. How about this? Example, converge or diverge? 1 plus a 4th plus a 9th plus a 16th plus a 25th plus dot, dot, dot.
I think that diverges.
It converges. It's 1 over n squared.
Yeah, so you have to first come up with a formula for it, right? You need to come up with the formula that creates this series. So this is where you have to realize that Chris, I think, saw it, that this is like 1 over 1, 1 over 4, 1 over 9. All of these are squares, aren't they? Perfect squares. This is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So we have to look at this being 1 over n squared. And check for yourself. If you let n be 1, you get this. If you let n be 2, you get that. Let n be 3, you get that. And this is a P series, isn't it? With your P being 2, which is bigger than 1, which means we have convergence.
Isn't they are all going towards a 0 if the number gets bigger?
Yeah, but that has nothing to do with the series. Remember, don't confuse the nth term test. What you just did was the nth term test. All these do go to 0, but that doesn't tell you anything about the series. You're still looking at it from the perspective of what the sequence of numbers is doing. That's not
Yes.
what we're interested in,
Because
right?
series is like the sum of sequences.
That's right. That's right. Okay, what about this one? Same idea here. Convergence or divergence here. 1 plus 1 over root 2 plus 1 over root 3 plus a half plus 1 over root 5 plus dot, dot, dot. So what you need to do here is see if you can come up with a formula for it.
1 over the square root of n.
1 over the square root of n. Right? Because this is really, that first one is like 1 over the square root of 1. 1 over square root of 2, square root of 3. Oh, guess that 2 is actually square root of 4. So it's a little tricky there, but see, it's all squares, square roots. So this is a P series, right? What's P?
1/3 or 1/2, sorry.
1/2, and that's less than 1. And anytime you have less than 1, you have divergence. That is a divergent series. Questions? All right, so now we get to the next test. See, this isn't really a test. I mean, it is, but it's not really. It's just like you just look and you recognize, oh, it's a P series. Oh, you look at the value of P and that just tells you, you know, P less than or equal, P less than or equal to 1, you have divergence. P bigger than 1, you have convergence. So you're not really testing anything. You're just looking, right? Identifying. This next test is probably the one that kind of confuses people the most because they can't wrap their heads around what we're trying to do with this next test. So before I show you the test, I just want you to think about this, all right? Let's say that I have this. I have sum n equals 1 to infinity of something, a sub n, all right? That's a sub 1, a sub 2, a sub 3. We don't know what these are. They're just numbers, right? We're adding them up forever. All right, let's say that this is given to us. We're given this. All right, now, what if I told you that a sub n was always bigger than or equal to b sub n for all n, okay? So what I'm telling you is this. I'm giving you a series, right? Which is just the sum of all these numbers. And now I'm saying, what if I told you that each one of these guys, a sub 1, a sub 2, a sub 3, a sub 4, each one of those is bigger than some other sequence of numbers, okay? And I tell you that this series diverges. What could you tell me then? And why?
If b sub n diverges, that means it's less than 1. And if a of n is greater than b sub n, which is less than 1, it should be greater than 1.
Where are you getting 1 from?
Oh, I'm using the p series thingy.
Yeah, this is not P series. This is just a series in general. This is just a general series. So when I say this diverges, that means when you add all these guys up, right? When you add all these up, it's like blowing up, right? This thing is diverging, yes? But each of these guys, think about what this actually means. This means b sub 1 plus b sub 2 plus b sub 3 plus b sub 4 forever, right? If a sub 1 is bigger than b sub 1, right? Because that's what this says. And a sub 2 is bigger than b sub 2. And a sub 3 is bigger than b sub 3. And all of these add up to be something that's divergent, that's becoming infinite. Then what can you tell me about this?
That is convergent.
Divergent?
That it diverges as well to
Diverges.
infinity.
So all of these numbers right here added up become something infinite, right? And each of these numbers is bigger than each of these numbers. So this must also add up to be something infinite, right?
Yes.
It could be possible for this to add up to be something less than infinity because each of those are bigger, right? So that would mean, so if we're given this, and I told you that this was true, each of those guys was bigger than these guys, then if this thing diverges, the conclusion would be, therefore, the original series here, this one that we were given, must diverge. Does that make sense?
Yes.
Would that have worked? Would that have worked if I changed this to the other way around? I just want you to think about this. Don't write it down. What if I told you we had a series where each of these guys were smaller than each of these guys? This added up to be infinite. Could you then tell me that this was infinite?
No, then it would be
No.
convergent, right?
Well, it could be convergent. It may
But
not be.
it could
It may
also
still
be divergent.
diverge, but you can't say it's convergent, okay? So the direction of this inequality is very important here because it's telling us, look, if we're bigger, if each of these guys is bigger than each of these guys, and all these add up to be infinite, well, then those would have to be add up to be infinite also. But if you try it the other way around, you can't draw a conclusion, all right? Okay, so let me start over here. What if I give you a series okay, and then I told you that A sub n was smaller than or equal to B sub n for all n. See, so that's this inequality flipped over, right? And I told you that this sum converged. What could you tell me? So think about this. If all of the guys in green are smaller than all of the guys in blue, right?
Convergent.
And all these guys add up to be a number, and these guys have to be smaller, then these guys should add up to be a number, shouldn't they?
Yes.
What
Yeah.
if they add up to like negative infinity?
Okay, so one of the conditions here is that these are positive. These are positives. Okay, so
Oh,
I
okay,
haven't
yeah.
thrown that in, but very good observation. We do have to assume that these are all positive numbers, because if you did have negatives, this would not be true. Okay, so then you would say, therefore, the original series would converge. Okay, I hope you understood that idea. Now let's look at the actual comparison test. Okay, here's the test. So let me try and explain what's happening here. It says, all right, suppose we have this series that's given to you. Okay, that's the problem that's presented to you. And Chris, I think you brought up the negative thing, and that the series you're looking at is always positive. Okay, so we don't get any negatives that would screw things up. Then B sub n is this series you're not given. Okay, this is a series that you know. Okay, you know about this one. All right, you know about. I'm going to show you how this all works. So we have a series that's given to us that always has positive numbers in it, and then there's this other series that we've got in our minds that we know something about. Maybe it's a P series or maybe it's a geometric series, but we know what it does, okay? And it says, if the series that you know about converges and all of the A sub n's are smaller than the B sub n's, then the original series converges. On the other hand, if the series that you know about diverges and all of the A sub n's are bigger than the B sub n's, then you're going to have divergence of the original series. Okay, that's basically what I just said. That's basically what I just said right here. Suppose we're given a series, and I told you that all of these are bigger than all of these guys, and that this adds up to be basically infinite. Then that one must be infinite. On the other hand, if you're given a series and you know that all these in green are smaller than all the blue ones, and this series converges, well, then that one does too. That's exactly what the comparison test is doing, all right? Now you have to see this in action, all right? Because this is somewhat challenging to put together. All right, so let's do this one. Let's try and figure out whether or not this converges or diverges. Sum n equals 1 to infinity, 1 over 3 to the n plus n squared. All right, let's start running through some things. I'm not going to write all these down. Nth term test, right? That's where you just take the limit of this as n goes to infinity. What do we get?
0, fail.
0. That test fails. Okay. Is it geometric?
We can say, but then we have addition in between.
Yeah, so we can't split that into 2 different ones, can we? Because there's 2 terms on the
Yeah.
bottom. So it's kind of geometric. Do y'all agree? It's kind of geometric. Like this part's geometric. If it was just 1 over that would be geometric. But it's that plus n squared that's not making it geometric. So it's not geometric. Definitely not harmonic, right? Not harmonic. Telescopic, I need to be able to factor or do something to create 2 terms for subtraction. Can't do that. Is it integral? Do you want to do an integral test on this? Do you feel
I
like
think yes.
Do you want to
I
integrate
think-
that? I don't want to integrate that.
Oh,
I don't think we could integrate that, honestly.
so basically, in order to do the integral test, we first try to think if we can integrate it, and then
Absolutely.
we find the continuous and everything.
Yeah, yeah. I would not go show all the things and then say, oh, by the way, can I integrate it? I would always start with, do I want to integrate that? And I don't want to integrate that. Let's see.
Yeah,
If I were to go to Wolfram, why do I not have Wolfram up there? I just don't understand why I don't have it up there. So if I go to Wolfram and I ask it to integrate 1 over 3 raised to the x plus x squared. Whoa, wow. No result found in terms of standard mathematical functions. Now, it did give me a series expansion of the answer. This is where we're headed. We want to be able to do this. We want to be able to get this because we don't want to ever be stopped because we don't know how to integrate. And so the ultimate goal of chapter 8 is to be able to take something like this and still be able to do the antiderivative. We seem very far away from that still, don't we? We are very far away from that still. Okay, but all right, so not nth term test fails, geometric no, harmonic no, integral test no thank you, and p series, is it a p series? Is it 1 over n to the p?
No.
That is right, but this is there too. We can't ignore the fact that we have a 3 to the n. So p series can't use. Ready? So comparison test. So here's where you have to, okay, that's you, have to figure out what to compare this to.
I have a question.
Yeah.
Can I bring out a 0, an imaginary 0, and try to separate it?
You're not gonna be able to split that denominator up. There's no way you can split it into 2. Just properties of fractions. You're just, if you have 2 terms in the bottom and 1 on top, you can't split it. You can try hidden stuff, but it's not gonna happen.
Okay.
Yeah. So this is okay, so this is the hard part. I'm about to do the comparison test, all right? The way the comparison test works is that you have to start with what you're given, okay? So this is what I'm given, and that means that this is the a sub n, okay? That's the sequence for that first series. I, you, us, we have to come up with something to compare it to. And whatever we compare it to, we better know what it does. Okay, we need to know what it does before we even write it down. So when you look at this, I think we all said it's almost like a geometric because of the 1 over 3 to the n, but then it's almost like a p series with the 1 over n squared, right? Which of these things do you think are more dominant? As n gets bigger, do you think the 3 to the n is more powerful, or do you think the n squared is more powerful?
N squared will be more powerful.
Sure. Just think of a number. Just take a number like, I don't know, 10, right? 10 squared versus 3 to the 10th. Which one of those is going to be bigger?
The other, yeah,
So
through the
3 to
end.
the 10.
This exponential will dominate the quadratic, won't it?
Mhm.
So what I'm going to guess right now, and this is purely, it's not a just blind guess, but it's a hypothesis kind of I have, is that I want to compare that. I want to compare that to this. Because I'm saying that like when n gets really big, this n squared doesn't matter as much. So I'm comparing it to this. So this is my comparison. And this right here is my B sub n. Now, can somebody tell me what type of series this is?
1 over P, the NP.
It's not a P series.
Uh,
Because for a P series, you have the n is down on the bottom and the P is up top.
Geometric.
It's geometric, right? If you look at it this way, it's really like 1/3 to the n, isn't it?
Yes, 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 yes.
Now, it's not, it doesn't say -1 up there, right? It doesn't? Like it doesn't say -1, we need that to say -1, but we could make it do that, couldn't we? I'm not going to. I'm not going to. All I really need to know is whether or not that number right there is what?
Less than 0 or
Less
1.
than
sorry.
1, 1.
Okay, so R for us would be 1/3, and that is less than 1. And what do geometric series do when the R value is less than 1?
Converge.
It converges. Okay. Let's back this up. We have our original series. We didn't know what to do with it, but we think it looks kind of like this one, right? This one is a geometric series that we know what it does, right? This is a geometric and it converges, right? So we are going to compare our series that we started with a convergent series that we think it's kind of close to. Go with me?
Why did you choose 1 over 3?
To the end?
Yeah,
Because I think that when we look at this, the n squared does not have as much of an impact on this expression as the 3 to the n does. When n is really big, this n squared really doesn't matter. So I'm kind of guessing, okay, maybe I can just compare this series to this one.
okay, so we find out for the one which has the most impact on the series.
Yeah, that's a good kind of rule of thumb. It's not always going to work, but it's going to work most of the time. All right. All right, so let's play this thing out. Again, we have given our series and we found something to compare it to, and that series converges. All right, let me go to the note. If the thing you're comparing it to converges and this is true, then the original series will converge. That means I have to figure out whether or not that's happening. I need to know, are my A sub n's always less than or equal to my B sub n's? Y'all see what I have a convergent series I'm comparing it to, but I need to check that this inequality is true. So now what I'm going to say is I want to show that A sub n stays smaller than or equal to B sub n. If I can show this, I'm done, because then whatever this one does, this one does. Okay, so A sub n is this. Is that, this is a question, is that less than this? Yeah, you could just cross multiply right now. And then you can just subtract 3 to the n on both sides. You get 0 is less than or equal to n squared. And is that true? Is that true? Absolutely true. N
So we
squared
can-
will always be bigger than 0.
We can basically use any of the greater or the lesser than sign, and then we can find out if it's either one is true or false. If one
You
is
don't
false,
have you don't have a choice on that. You do not have a choice on that symbol. That choice is dictated by the actual steps. If you have converged, so if the thing you're comparing it to, right? This is what we came up with, right? We came up with this. we happen to choose a convergent series. That means this is the inequality we must show. Had we found a divergent series to compare it to, then we would have had to have shown the inequality works the other way. Which if you tried, it wouldn't. Like, I promise you, go try and find something to compare it to that's divergent and show that's true, you're not gonna be able to. Let's just keep working because you got to see a couple of these to start to catch on. All right, so at this point, I can draw my conclusion. Therefore, the original series converges by the comparison test. All right, I'm going to move on. We're going to do the same problem. Okay. So somebody else comes in here and says, okay, you know what? I think I want to compare that to this. So, all right, you know what? They, whoever came up with that to compare to, they were thinking, you know what? This looks a lot like 1 over n squared, and they're ignoring the 3 to the n kind of. They're saying, you know what? I think that it looks more like that. What type of series is in red? What type of series is that?
P,
P. Okay, what's P here?
2.
2. 2 is bigger than 1.
Yes.
What happens when you have a P bigger than 1?
Convergence.
You get convergence. Okay. So I am taking a series that I know what it does. It's convergent, right? And I want to compare it to that one. What inequality must I show? Well, I found something that converges, right? It was a P series. It converged. P was 2. So I need to show that this inequality is true again. Let's see if we can show this. We may not be able to. So I want to show that a sub n is less than or equal to b sub n. So I want to show that 1 over 3 to the n plus n squared is less than or equal to 1 over n squared. Right? Let's cross multiply again. Let's subtract n squared on both sides. Is that true? Yeah, 3 to the n is bigger than 0. Therefore, the original series converged. So I guess I hope what you just realized is that there's going to be more than one way to do these problems, which means every single one of you is going to possibly do something different, right? Each one of you is going to potentially do some comparison that maybe another student doesn't do.
Okay.
Okay. Let's do one more. Oh, well, we're gonna do a couple more, but I want to do one kind of on that same line of thought. So I changed the problem a little bit. Instead of using n, I used n. I'm sorry. Instead of using n squared, I did n here. That's our original series. So let's say that I want to compare it. You know what? Why don't you? I'm going to go refill my drink. Why don't you sit there and think about what you'd like to compare that to? All right. All right, anybody want to share with me what they're going to try?
I was looking for 1/3 to the n because like it had the biggest impact.
Okay,
So I was, so this is convergent.
yep, this is geometric and it's convergent. Okay, what inequality do you have to show?
No, less than and
Yep.
equals to.
We need to show that the one on the left there is less than or equal to the one on the right. Which if you cross multiply, it works because you can subtract and that's going to be true. Therefore, this converges, right? Okay. Now, what if somebody else decided to do this, 1/n? So they did the 1/n instead. What type of series is this?
Harmonic.
Harmonic. What does it do?
Divergent.
It diverges, okay? So if we're going to compare it to this, so look, we're doing the same problem, but we're doing a different comparison, just to show the difference. Since this is divergent, the steps say that if we're divergent, we're comparing to something that's divergent, we have to show the inequality is true this way. Let's see if we can show that that inequality is true. Is 1/3 to the n plus n, is it bigger than or equal to 1/n? And now cross multiply. Subtract n. Is this true?
No.
No, this is not true. Okay, let me just recap. We started with an original series. Somebody decided to compare it to that. And when they worked the inequality out, they got this. What does that mean?
That it's not divergent.
Not quite. It means the test fails. In other words, your choice of something to compare it to wasn't good enough, which means you better pick something else.
So yes, initially I had the same question. Like for example, I pick something wrong and I compare it and my test fails. So that means if my test fails, then the other option would be the next best alternative would be the correct answer.
Well, hopefully, right? Hopefully it would. The thing I want you to take away from this is that if you go through the work and at the end your inequality is not true, you cannot draw a conclusion from that. You cannot determine, oh, then it converges, or oh, then it diverges. What you can conclude is that your test, the sequence or the series you tried to compare it to, couldn't give you any information. It's almost like a failed pregnancy test again.
If we do it right.
What's that?
If we do it correct, our test. So what would happen? I don't know too much about this, Professor, but what will happen if you compare the 1/3 to the n plus n to something like n to the n minus 1, for instance? Is that even possible?
You want to compare that to, what?
I just want to pick something that is not something 1/n or 1 over something totally different.
Okay,
Call
so,
it, yeah, something like that, or a, yes,
so
or
here's the
one
thing.
number.
Whatever you pick right here, whatever you pick, you better know what it does, right? Because if you don't know what this does, then you can't run the comparison.
Okay.
You're always trying to pick something that you know what it does, right? Like I picked this because I know it's geometric and converges. I picked this because it's harmonic and diverges. I don't want to ever pick something and be like, well, I don't know what that does, because then I can't conclude the green or the yellow here because I don't know what the thing I'm comparing it to it does, right?
Okay.
Does that make sense?
Mm-hmm.
Let's do another one. All right, nth term test. Don't forget, always run your nth term test real quick. Let n go to infinity on that. That goes to 0, right? So that test fails. It's not geometric. It's not harmonic. It's not telescopic. It's not a p-series. I don't feel like integrating that. I don't think you do either. So maybe we can compare it to something. Anyone got something for me to compare it to?
N over 7n cube.
10, what did you say? 10 over 7n cubed?
Yes.
Okay. Do you know what that does?
I'm figuring it out. So I think it converges
Okay. Why? What
because
type of language is that?
as n goes bigger, it's going to be bigger, like if it goes to infinity, for example. So yeah, it's going to be a 0.
I would throw an eraser at you if I could right now. I'm joking around with you, but I really want to drill it because you cannot look at this and say, what does that go to? If that goes to 0, we don't know anything about the series.
Okay.
I only said that because I want you to remember it. Again, he said he was going to throw an eraser at me. Okay, I really want you to remember that when you look at these series, knowing what the formula does here, knowing what this does, tells you nothing about the series.
So,
Unless it goes
whenever we're gonna,
hold on, unless it goes to something other than 0. Like if this limit right here went to 1, we'd be done. This is going to be divergent. But it goes to 0, which tells you nothing. Abe?
so in order for us to determine something to compare it to, we need to know the rules basically of this.
Yeah, you need to pick something that you know what it does, right? Now, we do know what this does because this right here, 10 over 7 is like a constant. Don't even worry about the 10 over 7. You have 1 over n cubed, right? Basically.
It's geometric.
N has to be in the power. N has to be in the power to be geometric.
So it is p-series.
It's p-series. Because the power is 3, right? P is 3. Bigger than 1. That gives you convergence. So Mustafa he picked a good series for us because it's a p-series, right? It's a p-series. Mustafa, do you see though, it converges not because this thing goes to 0. It converges because this is a p-series with p being 3. That's why it converges.
Okay.
Are we clear?
Yeah.
Okay, good. I just don't want y'all making that mistake. I think I said this in the very beginning. The biggest mistake I see by students when they're dealing with series is they look at what happens here as n goes to infinity. And if it goes to 0, they say that the series converges. And that is the biggest mistake you can make because if it were that easy, then series wouldn't be hard.
Yep.
But it's more than that, right? It's adding them up forever. Okay, we have a convergent p-series that we are comparing this to. So what must we show? We want to show that the a sub n and b sub n are related, but how does the inequality go here? If this is convergent.
Less than or equal to.
Less than or equal to. We need to show that's true. Okay, so let's try it. 10 over 7n cubed plus n squared plus n less than or equal to 10 over 7n cubed. Cross multiply. When I say cross multiply, we're not actually cross multiplying. I hate that phrase, cross multiply, but most students, they understand what I mean when I say that. We're actually just clearing the fractions out. We're multiplying both sides by the common denominator, and that's what happens here.
The first time you said that, I actually thought like you meant cross multiplying, and I kind of looked at your result and I was like, that's not right. That's not actual cross multiplying.
Yeah, it's a term that is used a lot in algebra that I can't stand. But if I were to sit here and be like, let's clear the fractions by multiplying both sides by the LCD, then it's just, at the end of the day, I mean, I'm just multiplying that times that and that times that. That's all I'm doing. You know,
Mhm.
it's the same. The algebra comes out the same. So, okay, now I'm going to subtract this on both sides. So I get 0 less than or equal to 10n squared plus 10n. And I think we're all okay with agreeing that that's true.
Mhm.
Yes?
Yeah.
Okay. Done. So what happens? Therefore, that series, I'm not going to write it again, converges. All right.
So what if we select? What if I selected 10 over n?
Okay,
It's the
let's see
same
what
thing.
changed. If you did 10 over n, right? If you did 10 over n, you'd be comparing it to 10 over n. That's harmonic, right?
Yes.
That diverges. And so you would have to show the inequality holds the other way. So you'd have to show that 10 over 7n cubed plus n squared plus n is bigger than or equal to 1 over or 10 over n. And I'm pretty sure you're not going to be able to show that's true. Because you'll multiply
Yes.
both sides, you'll get like 10n on the left. Other side, you're going to get this huge cubic polynomial, and it won't be true. Which means the test failed. Like again, that wouldn't that right here would mean the test fails. You could not conclude then that this thing converged.
By looking at the series, cannot we just like have an idea if it converges or diverges just without any test? Like if we let it go to infinity, that this whole thing, 10 over 7 cubed plus n squared plus n.
No, you can't. Because the fact that that goes to 0 does not determine the convergence or divergence of the series.
True.
I keep saying this over and over. You cannot, look, if it were as simple as us just looking at this and saying, oh yeah, that goes to 0, it converges, then you wouldn't need all of this. You wouldn't need all this, right? You just be, oh, it goes 0, it converges. That's not the case. Look, let me give you another example, all right? Let's look at this one. I hope I'm not coming across as being mean. Or
No,
anything.
no, no. This is actually complicated, but I don't see the big picture yet. But yes, practice will give us that.
No. Because this is kind of, going against the things that I've been dealing with in other sections when like improper integrals or squeeze theorem. So it's like kind of confusing.
Yes, this is. I mean, first time you see this, this is going to be weird. So look, let's go with that logic right now. If we look at this, do you have an instinct as to whether or not this converges or diverges?
I think it's kind of different now. So it's infinity over infinity right now.
What will be your approach, Professor, to determine that?
To determine what?
To determine if it converges or diverges.
Well, I have to go through the whole set of process. Look, we have this right here, just that. Forget the sum. That right there. If I take the limit of that and let n go to infinity, I'm going to get infinity over infinity. And after I do L'Hopital's rule a few times, I will find out that that goes to 0.
Okay.
Okay, that goes to 0 if you do L'Hopital. Now, that does not mean that the series converges. Doesn't.
No.
In fact, this is going to diverge. All right? This is going to diverge. Now, the question is, how do we show it? Right? How do I show? Right now, I have no idea that it converges or diverges. I have no idea. No idea. The
Mhm.
pregnancy test failed, right? This thing goes to 0. I don't know anything else. Then that means I know nothing. So I need to figure out what to compare it to. So this is the part that is the challenge. You've got to figure out what you think that most resembles, and whatever you think it resembles, you need to make sure you know what this does.
N cubed divided by 1, -1,
N cubed divided by what?
-1.
So you think that this n to the 4th doesn't really matter? When you look at all of these, which of these terms, n cubed, n to the 4th, or -1, which of those is like the most powerful dominant term in the entire thing?
N to the 4th.
N to the 4th, for sure, right? N to the 4th. Now, n cubed does play a role. This -1 really doesn't make much of a difference. Do y'all agree?
Yes.
So look, would this seem reasonable for you to be like, look, the -1 really doesn't matter too much. It's really kind of like just n cubed over n to the 4th. That's really kind of what it's like.
Yep.
And that's just 1 over n, isn't it?
Mm-hmm.
Okay, so that's harmonic. And that diverges. Now remember, this is kind of a guess, everyone. I'm guessing as to what I want to compare it to. By looking at this and just kind of going, this is kind of what I think it kind of looks like. It's not a just blind guess, right? It's an educated guess, but it's got to be something I know what it does. Now, what inequality must I show?
Greater than?
Greater, right? I need to show this inequality is true. So I want to show that n cubed over n to the 4th minus 1 is bigger than or equal to 1 over n. Clear the fractions by multiplying both sides by the LCD or cross multiply.
Mm-hmm.
Subtract n to the 4th on both sides. And voila, that's true. So whatever this does, that does, right?
Yes.
So this diverges. So that diverges.
So what you're saying there is that the series diverges, but the sequence converges.
Yes. Yep.
Okay. So in other words, if it says the sum from n equals 1 to infinity, that you can think series. And if you think series, you can say that it's like the points are all added together.
Mm-hmm.
Instead of being separated.
Yeah. So we know that each of the points, right? Each of those points, that's the sequence. We know that each of those points is getting smaller and smaller and smaller and smaller. But as we add them together, the sum is actually getting infinitely big. That doesn't always happen. Sometimes the sequence numbers get smaller and you add them together and it converges to a number.
Mm-hmm.
The thing about a series to kind of keep in mind is this, right? This piece right here is the sequence, right? The whole thing is the series. If the sequence goes to 0, you know nothing, okay? You know nothing, all right? You know absolutely nothing. If the sequence goes to something other than 0, then and only then can you say that the series diverges. We haven't had that. Every single problem I've given you, the sequence part of it goes to 0, which then meant we had to go do other tests.
Okay.
Okay. All right, so this problem that I just did right here, I'm going to change one thing on it, and I want you to see how that creates some chaos. All right, you ready?
Mm-hmm.
You take a little breath. You don't have to take the breath. Okay, n cubed over n to the fourth plus 1. I only changed one thing, didn't I? I did +1 instead of -1.
Mhm.
Okay, well, let's just run with that same logic that we had. This does look a lot like this, doesn't it? Still, that +1 shouldn't make that much of a difference. And this is still harmonic, so that diverges. Everything's still the same there, right? So I want to show that the sequence there is bigger than or equal to the sequence there, right? So I want to show that n cubed over n to the fourth plus 1 is bigger than or equal to 1 over n. Clear things out. N to the fourth, bigger than or equal to n to the fourth plus 1. Subtract n to the fourth. Uh-oh,
The test failed.
that's not true. The test failed, exactly, Abe.
So
The
just
test,
by +1.
I'm sorry?
Just by changing the -1 to a +1, it failed.
Mm-hmm.
Because it's just a different series now.
Yeah, it's different. So this could be very frustrating, right? So I want you to just, I want you to see something. If we go back to the last problem, right? The one that had the -1, right?
Mhm.
This is what we did. And when we cross multiplied here, or whatever, clear the fractions, it worked because this was a -1, didn't it?
Yeah.
This was a -1, and then these went away, and this side was bigger than this side, and we were happy, right? We were
Mhm.
happy. But here, because this is a +1, when we cross this and multiply like that or whatever, this side now is bigger than this side because there's a +1 there, right?
Mhm.
You're going to be pissed at me for doing this. Watch. Do you agree that this would have worked had that been a 2, maybe in front of that n to the fourth? Think about it. If that was a 2, if it had been a 2, it wasn't, but if that had been a 2, then the next line I would have subtracted n to the fourth on both sides, right? And then I would have had n to the fourth is bigger than or equal to 1, and that would have been true, right? Wouldn't that have been true? Okay. Now, could I have made that 2b here? Let's go to the step above that. How could I have made this be a 2 n to the fourth? What would I needed to do?
Double the other side? No.
No, yeah,
So-
over 2n.
I would need this multiplication here to here to become a 2 n to the fourth, right? Now I can't do anything to this because that was given to me, right? I have no control over the blue, but I have complete control over this one, don't I? Because I get to choose that. So if I put a 2 here down here, right?
Mhm.
Then I go back to this, I change that to a 2 and change that to a 2. Is this still harmonic?
Yes.
Does it diverge still? Absolutely, right? But now does the inequality work?
Yes.
Yes.
So you can get the test to fail, but you can still like backtrack and try to
Reverse
force it to
engineer the
work.
correct series.
Click
Yeah,
it.
you can like backtrack and figure out what you would need to make it work. Welcome to
I
series. I
mean-
mean, this is the way it is, you know?
So if wasn't like, if it wasn't a 2, it was like an n squared, just saying hypothetically, that, but wouldn't it change the whole sequence?
Yeah, great question. Let's do that, okay? Let's say that you did this problem and you're like, shit, 0 is not bigger than 1. So then you go, all right, let me try, maybe 1 over n squared will work, right? Maybe you're like, okay, I'll do that because I'll just try and make this I think what you're saying is like, if I make that an n squared right there, then when I cross multiply right here, I'm gonna get an n to the 5th, and that'll be bigger than the other side. So maybe that'll work. But we run into a problem almost immediately, because now what type of series is this?
P
This is a P series, right? And what does it do?
converges.
It converges. P is 2, it's bigger than 1. Now we have a convergent. Now we have a convergent series we're comparing it to. So what inequality do we have to show?
Greater.
That this is small, hold on, yeah, this is smaller than this, right? Because we're comparing it to a convergent one, so we need this to be smaller.
Okay.
And now when you set it up, everything's gonna fall apart. Like, it's not gonna work. Because now when you do your little cross multiply, you get n to the 5th less than or equal to n to the 4th plus 1. And well, there's different ways you can show this, but I don't know. Maybe we could just convince ourselves that this side is gonna is no way, like, there's no way that this side will be big, smaller than this side. Like, eventually n will get big and this will dominate the other side, right? So
What if we
doesn't-
divide a n, like the part where we have a control over, the 1 over n square, and we do multiply by 1 over n?
we're here?
Yes.
Well, we did that. That's what we started with. We did 1 over n. 1 over n didn't work. So then we had to like reverse engineer a 2. 1 over 2n does work.
Okay. What if instead of doing that, reverse engineering it and take n cubed to divided by n, or divided by 1?
N cubed divided by 1?
Yes, if I choose that instead of just reverse engineering it.
You want to do this compared to just n cubed.
Yes.
All right, well, first, this does diverge. Not because it's a P series, but because when you do the n term test and you take the limit of that, it goes to something other than 0. And so you can tell me that this does diverge. That does diverge. So if this diverges, then what you need to show is that this is bigger than this. So you need to show that n cubed over n to the 4th plus 1 is bigger than or equal to n cubed. And when you cross multiply, it's not happening. N cubed is not bigger than n cubed times n to the 4th plus 1. That is not true. And therefore, that test fails.
Then we have to reverse engineering that part too now.
I don't think you can fix that. I mean, this one I could fix by just putting a number in here. But this, I don't think I could ever do anything to manipulate it enough.
So in this case, whatever we choose is going to make sure that the test is failed. So need to like, oh my God, this is so confusing now.
Yeah. Well, now that you are all masters of the comparison test, I'm just kidding, right? You have to go practice, right? There is another part of the comparison test that's in your notes here that I've conveniently skipped over. There is a third part to this test. It's separate, okay? So the way you look at this is that you're either gonna be doing one of those two, okay? You're either gonna do one of these two, or you can do something completely different. And I hate to save the best for last, but this right here is probably one of the most powerful comparison tests that is out there. And once I show this to students, they get all pissed off at me for not showing them this in the beginning. Okay? What this says is that we still have to start with the series that was given to us. We still have to come up with a series to compare it to. We still have to know what that series does. But instead of trying to figure out all these inequalities and what works and all that, all we have to do is take the limit of the two sequences. So what that says right there is we're going to take the limit as n goes to infinity of the sequence of the first series divided by the sequence of the second series. And what we're going to do is see if we get an answer. If this limit, if this answer we get is a positive real number, so it can't be infinity, it has to be a positive real number. So if we get a positive real number, then whatever one series does, they both do. So if one of them diverges, they both diverge. If one of them converges, they both converge. So let's see this in action. You ready? I'm going to go back and do the problem that we just did. This one right here that caused a little bit of problems, right? N cubed over n to the fourth plus 1. Right. I'm going to choose to compare it to something. Here I go. Didn't we do that a minute ago? And
Yes.
didn't it fail? Didn't it fail? It did fail, didn't it?
Yes.
Okay, but I'm going to use the third version of the test, which is to not do an inequality and all that. Oh yeah, this diverges, right? That's harmonic. What I'm going to do instead is what we call the limit comparison test. And that means I'm going to take the limit as n goes to infinity of the first series sequence over the second series sequence. So I'm taking this guy right here, taking this one right here, and I'm going to take this limit and I'm going to see what it does. And what I'm hoping for is that this limit gives me a positive real number. So I'm just going to flip, right? I just take this 1 over n, I flip it up top, and that becomes an n to the fourth, or n to the fourth plus 1.
Mm-hmm.
Okay, now when we do this limit, we get infinity over infinity. So I'll just do L'Hopital one time. And when I do L'Hopital, I get 4n cubed over 4n cubed. And those just go away and just become a 1. Is that answer a positive constant? Is that a positive real number?
Yes.
Okay. So according to the formula, or according to the test, if that limit turns out to be some positive real number, then both series converge or both series diverge. So what do our series do?
Converge.
Oh, converge.
They diverge. They have to, because we know what this one does, right? That
Oh.
one diverges. This result being a positive real number means that whatever one does, they both do.
Okay.
So that
Okay.
means that one must also diverge. Wasn't that nice? Wasn't that nice?
It was beautiful.
That was nice.
But I'm guessing it's also situational.
Yeah,
Yeah,
it is.
I was gonna say, what's the catch? Why can't we?
No, and there's not a catch. It's really difficult to find problems where this doesn't work well. Sometimes it can be a little complicated. We're almost out of time. Let me go back to a problem. Let's look at this one. Look at this problem right here. Remember that? We did integral test, started, this was the second problem we did in class. Let's
Mhm.
take a look at this one right here, okay? I'm gonna go back and see if we can't do this with a comparison test. Remember, our conclusion from all this work was that it converged, okay? It converged. So let's see if we can't do it. It was n e to the negative n, which is the same as n over e to the n. All right, I'm going to try the comparison test. I'd like to compare this to maybe 1 over e to the n. I'm doing that because that's the same as 1 over e to the n, and that's geometric. And that's going to converge because 1 over e is smaller than 1. So we have a convergent series. Y'all okay with that? Okay, now if I try the limit comparison test, I'm taking the limit as n goes to infinity. I'm going to take this guy right here, and I'm going to divide it by the other one. Then I'm gonna do a little algebra. Flip it. And when I flip it, don't the e to the n's cancel? Yeah, right?
Mm-hmm.
And all I'm left with is n. And what does that go to? Infinity, right?
Infinity.
So what does this say happens if we get that? If you do this limit comparison, you must get a positive real number in order to say that they both converge or both diverge. Did we get a positive real number? Is infinity a positive real number?
No.
No. Okay, so it has to go to a fixed number. So what does this tell me? It fails. I was trying to give you an example where this wouldn't work, okay? Fails. How about this one? Remember we did this one? I'm really getting close to being out of room here, or out of time. Okay, if I were to do this one and I compare it, I would compare it to 1 over 3 to the n, because that's geometric and it converges. And now let me try and run this using this test. So I take 1 over 3 to the n plus n squared over 1 over 3 to the n. I flip, all right, I reciprocate things. I get 3 to the n over 3 to the n plus n squared. And if I do that and let n go to infinity, I get infinity over infinity, yes? So L'Hopital, L'Hopital, shoot. The derivative of 3 to the n is itself times natural log 3 over 3 to the n times natural log 3 plus 2n. So go back to your Cal 1, derivative of an exponential function, a to the x, is itself times natural log of a. So that's all I'm using here. Now, if I let n go to infinity, I still have infinity over infinity, so I have to go L'Hopital again. And so on the top, remember this natural log of 3 is just a constant. So derivative of 3 to the n, again, I have to do that a second time, is going to be itself times natural log of 3, but I already had a natural log of 3 there. And on the bottom, I have 3 to the n, another natural log of 3, and I had a natural log of 3, so that's that one, and then plus 2.
Cannot they just cancel?
Not yet. We got to do one more L'Hopital. Because
Get
this
rid of
plus
2?
2. The plus 2 is preventing us from canceling, but if I do one more L'Hopital, I'll get 3 to the n again times natural log of 3, but I already had 2 natural logs of 3 there. All over 3 to the n, natural log 3, natural log 3, natural log 3, but now the derivative of 2 is 0. And now everything can cancel. And so you get 1. And 1 is a positive constant. And therefore, whatever one of them does, they both do. And this one converged, that means that one converged.
Why did it take so long for it to get canceled?
Well, because you have 2 terms on the bottom. So it's like, if I give you a fraction,
Oh, I
4
see.
4 plus 2, you can't cancel the 4s, right? So, you know, think about your next test, right? Your final, you're going to get a problem on there. It's just going to say, does this converge or diverge? That's all it's going to say. So, you know, you may do, I mean, you're going to be free to use whatever test you want. There's not going to be anything that says, oh, use the comparison test, or, you know, oh, for this, use the integral test. I know I'm out of time, but maybe I can just bring up a final.
Yeah, I can stick for that.
This is a final I gave last spring. rewrite as a rational number. In other words, rewrite this as a fraction. So you take a repeating decimal and rewrite it as a fraction. We've done that, right? Find the sum of this series. That's telescopic. Rewrite this in sigma notation. So first you have to figure out the formula that creates this, then figure out if it converges or diverges. But I don't give you any like indication as to what method to use. So this might turn out to be geometric or harmonic or telescopic, or you might have to run an integral test or maybe a comparison test. That's about all you would be able to do on the final at this point, just those first three. Find the radius of convergence, interval convergence, power series, Maclaurin series, Taylor series, power series. Integrate something that you can't do on a computer. Bonus, find the radius of convergence. Yeah. So of the 10 problems on the final, 3 of those right now you could probably handle.
Wow.
Yeah.
Yikes.
Yeah, so we still have a lot to do, but it's just one step at a time, one foot in front of the other. So for now, what I would do is see how you do with the homework for the section, what is it, 8.3?
Okay.
Yeah, it's 8.3. Yeah. So you should be able to at least attempt all the homework for
We're gonna
8.
have a fun holiday weekend.
Well, Thanksgiving's
weekend?
the next week. So this weekend you don't get a break, right?
Mhm.
You're
Nor the
all
other, yeah.
upset.
All right.
Even then, it would be a very, very enthusiastic Thanksgiving.
Exactly.
I would think.
So now that you're seeing this stuff, I think you're starting to understand why it is that Chapter 8 is such a monster. It's so new, like it's so different than any math you've done, right? Like there's nothing that's, I mean, of course there's little pieces, but just the logic involved of, oh, okay, I have to show this. That means I have to show this inequality. And, oh, you know what? That doesn't work. Maybe I'll tweak it. It's not as cookie cutter. It's not as like mechanical. It's very much kind of open thinking. So, all right, well, good luck. You have my homework solution videos out there. Try and get through as much as you can. We'll come back. We'll hit 8.4, which will be, we're going to finish off these tests. We still have the ratio test, the almighty ratio test, the almighty. This is the best test on the page. This is the best test. This is it right here. When it all comes down to it, this test is the one we will use the most. The root test, alternating series test, and then this last little thing. So we still have a couple to go through. All right, have a good day. I will see you on Thursday, right?
So the final is more Chapter 8.
I said the weekend, didn't I? Did I say the weekend? I think I'm wishfully thinking that like today's Thursday. We still are going to meet on Thursday, aren't we?
Yep.
Yeah, so I'll see you on Thursday.
Cool.
Okay. So final is more Chapter 8 based.
Almost, I mean, it's practically the whole thing, right? Because look, I mean,
Didn't we start at 8.2?
I'm sorry?
Didn't we start at 8.2? And I don't know how far we're going to get, but.
Yeah, I mean, when you think back to 8.1 now.
Right.
That's,
I mean, there's not much in 8.1 that's not already built in here, right? Taking limits of sequences. I mean, we do that every time we run an nth term test, right? The first test we do is basically what 8.1 was about. It's also the whole idea of like coming up with a formula. It's right here. So yeah, this test basically starts at 8.2, 8.2, 8.2, 8.3, 8.5, 8.6, 8.7, 8.8. Yeah, so it's all Chapter 8, pretty much.
okay.
Okay.
Yeah.
All right. Thank you, sir.
Okay, you'll have a good one.
Yeah.
Can
Thank
I
you very
ask
much.
can I ask a question about the exam?
Yeah.
Specifically 6C, that
Oh, yeah. Mhm.
series, that sequence, sorry.
Yeah.
Can you
You-
like
Can you show me how you did that one? Because
give it up? Yeah, that one, like, dude, I went to Wolfram and everything, and I couldn't get it. I just couldn't get it.
Let me
I
see.
mean, it took a while, but I think I had it.
Where the hell is it? Okay, all I did,
Didn't it like have a factorial in it? Yeah.
Oh, it did.
you had to realize that the numerators were factorials. And so the way I guess you can look at it is, let me just see here. Yeah, I've got the biggest headache. Okay, so I think the first thing is that you understand that you've got alternating, right? So that takes care of the alternating. Now, you start to realize that all the denominators are powers of 3.
Mm-hmm.
So if you kind of have to kind of guess at this as to where it starts. So if you make the appropriate guess that this first one is 3 to the -1, this one would be 3 to the 0, 3 to the 1, 3 squared, 3 cubed, 3 to the 4th. You can see that if you do this, it doesn't match up with these denominators. But that's because there's something from the numerator that's canceling.
Yeah.
There's a reduction of the fraction, a reducing of the fraction. So then what you have to do is kind of see what you need to rebuild things. So this right here is that number. Let's forget the alternating, okay? This right here, 3 to the -1 is 3, okay? This one, 3 to the 0s is 1. Okay, so that's okay, or 1 over that. And then this one means that I would need to have a 2 on top, right? Because 2 over 3.
Mhm.
Here I need a 1 on top. So 1 over this would be 1. 1 over this would be -3. 3. This one right here, what would I need on top? Because the bottom is really a 9, right? Like if I follow this pattern, the bottom is a 9, but it
Yes.
needs to
3.
be a
You
3.
need a 3 up top.
So I need another,
Six.
I need the 3. So this needs to be a 6. 6 over 9 would give me 2/3. This one is a 9, but this is really 27. So again, there's a 3 that went away. So I need a 3 on top. So that would be 24. Is this making sense?
Oh,
And then this one-
crap.
Off by 3. So you'd have to have 120 up there.
In my sequence, I thought it was 1 over 3.
Yeah. Well, this right here, this sequence of numbers is factorial. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, and so on and so forth.
I spent hours on that problem.
That is a hard problem. Trust me, I made that because I knew it would be challenging. But I also only made that problem worth 15 points, and that was 1 of 3 problems. So I was hoping you would kind of like balance your effort based on like how hard do you want to work for that. But I wanted to push people, so.
Wow. Yeah, yesterday when I spoke to you, it was that question that I had, and then it was this one. And it's funny because after we talked, I was like, there's no way I'm going to spend all day on this one question. Yeah, I didn't even do it. I submitted it blank because I just could not figure it out.
I at least tried it. I got close.
Another way you could have maybe approached this is to look at these, just like write the prime factorizations of these numbers. Like that's just 2 times 1. This is, let me do it backwards. 1 times 2, this is 1 times 2. This is 1 times 2 times 2 times 2. That's what 8 is, right?
Mm-hmm.
This one is 1 times, oh shit, you'd have to really break this down. 2 times 2 times 2 times, that's 8 times 5, right? The next one would be 1 times 2. So if you do the prime factorizations and then you start seeing, yeah, I don't even know if that would even help.
I mean, it was clicking at the time, but at the same time, the factorial was throwing it off.
I think maybe the cleanest way to do this
Like
There's
it's
different
funny
ways.
because I had factorial over 3, and then every time I tried to put it over some denominator, I couldn't get it to add up. But all I needed to do was just leave it as a factorial at the top and just let it cancel with whatever
Yeah.
the original denominator would have been. I was
Yeah.
so close.
I tried to go really big on these numbers to help you see that it's something growing fast, that it was a factorial, but you know, it's all relative. I don't know, maybe if I were doing this over, I would be like, okay, I think that's 3 to the -1. This is 3 to the 0. Like I said earlier, 3 to the 1, 3 squared, 3 cubed. So this is kind of me guessing as to what's happening in the denominators. Right? And then I just need to go in here and kind of make the numerators happen. So I think the first place you run into an issue, this is just a 1 on top, this is just a 1 on top, this is just a 2 on top. Here's the first place you run into an issue. That needs to be this. So what you're asking yourself is, how can I rewrite 2/3 as something over 9? And then to do that, you just multiply top and bottom by 3, and that's where you get 6/9. So this is 6/9. And then this one, you're like, okay, I need that to be something over 27. So 8/9 needs to be something over 27. So I'm missing a 3. I just need to multiply top and bottom by 3. So this would be 24 over that. And then you kind of do the same thing, and you start to see the factorial 1, 2, 3, I mean 1, 2, 6, 24. But you would have to recognize factorials. Like if you're not comfortable with all the factorials, I'm not sure you ever pick up the pattern 1, 1, 2, 6, 24, 120. I'm not sure you ever see it.
No.
All right,
Thank
I've got to
you.
run, everyone. I've got to be somewhere at 3. So
Thanks, Professor.
have
I
a good day.
appreciate it.
Thanks.
Have a good day. Take care.
Bye.
Nice day.